Along this lecture we find out the area of the green shape. In the drawing we have quarter circle AOB. We know that AD equals to DO. This is side OB. This is equals to 2 units in its length. And this is angle DCB. This is right angle. Again, our test is to find out the area of this green shape. The green shape, it is actually the right green triangle, triangle DCB. So we have to find out the area of the right green triangle, triangle DCB. So first of all, AOB is a quarter circle, and therefore this is a right angle. OB is the radius of this quarter circle, is equals to 2. Likewise, OA is also the radius of the quarter circle, is equals to 2. The radius OA that is equals to 2 has been bisected at point D into 2 halves. So the first half AD equals to 2 over 2, that is 1. And the second half, DO, must be also equal to 1 unit in its length. In the next step, we will complete this quarter circle to a circle. But before that, we will implement the Pythagoras theorem on this right triangle, triangle DOB. In this right triangle DOB, according to the Pythagoras theorem, in a right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendicular. So, in the right triangle DOB, here by PT is the relation for Pythagoras theorem. So in the right triangle DOB, dB squared, that is the square of the hypotenuse, and dB squared, that is the square of the hypotenuse, equals to d all square. Again, dB squared, that is the square of the hypotenuse, equals to d all square plus OB square. And again, in the right triangle DOB, according to the Pythagoras theorem, dB squared, that is the square of the hypotenuse, equals to d all square plus OB square. dB is the missing side, so we leave it as it is, so it is dB square equals to d all square. do is 1, therefore d all square is 1 squared, that is 1, plus OB square. OB is 2, therefore OB square is 2 squared, that is 4. So in total, we should find out that dB square equals to 1 plus 4, that is 5. So dB square, that is the square of the hypotenuse, equals to 5. Here we'll take out of this equation and find again that the length of the hypotenuse dB is equal to the square root of 5 units in its length. This is the hypotenuse dB, that is equal to the square root of 5 units in its length. In the next step, we will complete this quarter circle to a circle. So I completed the quarter circle to a circle, and we will extend the radius OB until it touches the circle. And we define the touching point of the extended radius BO with this circle. This point is point P. So, right side OP, it is actually the radius of this circle. Is equals to 2 units in its length. We will extend side CD by side line until it touches the circle. But the question is where the extended side CD will touch the circle. We will assume that the extended side CD will touch the circle at this point. So here we know that PB is the hypotenuse, PB is the diameter of this circle because of the fact that PB is a chord that passes from point O, that is the center of this circle, and we know that any chord that passes from the center of the circle, that is point O, must be the diameter of the circle. So PB is the diameter of this circle, so write it down. PB is the diameter of the circle. So, according to our assumption, we have here peripheral angle BC. We define the touching point of the extended side CD with this circle. This point is point Q. So according to our assumption, we have peripheral angle BCQ that is equals to 90 degrees in size, and peripheral angle BCQ subtend on chord BQ. Again, peripheral angle BCQ subtend on chord BQ. This is chord BQ. Chord BQ is definitely not the diameter of the circle because of the fact that chord BQ doesn't pass from point O, that is the center of the circle. And we know that only the chords that passes from the center of the circle are the diameter of the circle. And because of the fact that chord BQ doesn't pass from point O, that is the center of the circle, chord BQ is not the diameter of the circle. So we have peripheral angle BCQ that is equals to 90 degrees in size, and peripheral angle BCQ subtend on chord BQ that is not the diameter of this circle, and therefore we have a contradiction to all 5. Repeat quickly on all 5. According to all 5, any peripheral angle that is equal to 90 degrees must subtend on the diameter of the circle. In the moment we have peripheral angle MAB and MAN that is equals to 90 degrees in size, and therefore according to this all 5 peripheral angle MAN must subtend on MN, that is the diameter of this circle. Why? Because it is equal to 90 degrees in size. So according to this all 5 any peripheral angle that subtend on the diameter of the circle must any peripheral angle that is equal to 90 degrees in size must subtend on the diameter of the circle. Here we have peripheral angle MAN that is equal to 90 degrees in size, and therefore it subtends on chord MN, that is the diameter of the circle. But there we have contradiction to all 5. Why? Because we have here peripheral angle BCQ that is equal to 90 degrees in size according to what is given in the question, and still it doesn't subtend of the diameter of the circle, because BQ is definitely not the diameter of the circle, because it doesn't pass from point O, that is the center of the circle, and therefore cannot be the diameter of the circle. Due to the contradiction to rule 5, we will conclude that the extended side CD will not touch the circle at point Q. We will assume that the extended side CD will touch the circle at this point. When we find the touching point of the extended side CD with this circle, this point is point N. So, repeat again, the extended side CD touches the circle at this point, point N. Again, we have here correlation to rule 5. We have considered periangle BCN is equal to 90 degrees in size, and periangle BCN subtend on chord BN. Repeat again, periangle BCN subtend on chord BN. Chord BN is definitely not the diameter of this circle because it doesn't pass from point O, that is the center of the circle. So, due to the contradiction to rule 5, we derive that the extended side CD must touch the circle at point P and not in any other point. Okay. And again, due to the contradiction to rule 5, we derive that the extended side CD cannot touch the circle at any point that is near point P here, but it also cannot touch the circle at any point that is in the lower side of P here, and therefore the extended side CD must touch the circle at point P and not in any other point. So here we have periangle BCP that is equal to 90 degrees in size, and it subtends on chord PB, that is the diameter of the circle. Chord PB is the diameter of the circle. Why chord PB is the diameter of the circle? Because of the fact that chord PB passes from point O, that is the center of this circle. So, in conclusion, we found out that the extended side CD must touch the circle at point P and not in any other point, because if we assume that the extended side CD will touch the circle at any other point than point P, we will get a contradiction to rule 5. Now we don't have any contradiction to rule 5 anymore. Because we have periangle BCP is equal to 90 degrees in size, and periangle BCP subtends on chord PB, that is the diameter of the circle. Okay. So, in this right triangle PDO, PO equals to 2, DO equals to 1, we will implement the Pythagoras theorem on this right triangle PDO. Those two right triangles can go into each other. Because we have those two sides are equal to each other. This is the common side. And we have those two angles that are also equal to each other, because this angle equals to 90 degrees according to all three. All three says that the sum of the angles on one side of a straight line is equal to 180 degrees. So if we focus on the upper side of the straight line PB at point O, if the sum of the angles must be equal to 180 degrees according to all three. So which angles we have at the upper side of the straight line PB at point O? We have this angle that is equal to 90 degrees in size, plus this missing angle, because that must be equal to 180 degrees according to all three. Therefore, this missing angle must be equal to 90 degrees in size. We already found out that those two angles can go into each other according to side against side all. We have those two sides, they are both equal to 2 and therefore they are equal to each other. Those two angles are both equal to 90 degrees and therefore they are equal to each other. And side DO is a common side that belongs to both angles. Therefore, the hypotenuses of those two right angles must be also equal to each other, because they can go into each other. Therefore, the hypotenuse DP of this right angle DOP must be also equal to the square root of 5 units in itself, exactly like this right angle DOP, because those two right angles can go into each other. And those two sides are equal to each other. According to the rule, it said that corresponding sides and congruent triangles are equal to each other. Those two triangles can go into each other, and therefore those two corresponding sides must be also equal to each other in their lengths. But side DP is square root of 5, and therefore side PD must be also equal to square root of 5 units in its length. We can actually implement the Pythagoras theorem in this right triangle, but it's unnecessary because those two right triangles can go into each other, and therefore they must also the same corresponding sides. So side PD equals to the square root of 5 units in its length. In the next step, we will implement Rule 24 in our drawing. So a bit quickly on Rule 24. According to Rule 24 is true in any circle. So in any circle of chord AB intersects the chord CD at point O, then the following equation is true, that AO times OB equals to CO times OD. So in the drawing we have a circle, this is chord AB, that intersects the chord CD at point O. So in this drawing the following equation is true, that AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. So we can actually implement Rule 24 in our drawing. In our drawing, first of all, we will extend the radius AO until it touches the circle. And we define the touching point of the extended radius AO with this circle. This point is point Q. As I already mentioned before, we can implement here all 24. Why? Because this is called AQ. Intersects with this chord CP. At point D. The intersection point between chord AQ and chord CP occurs at point D. Repeat again. We actually found out that in our original drawing, chord AQ intersects with chord CP is point D. So all the requirements of all 24 are satisfied, and therefore can implement all 24. Only to all 24, the following equation is true. That AD times DQ equals to CD times DP. Okay, again, the following, according to rule 24, the following equation is true. That AD times DQ equals to CD times DP. AD is 1, times DQ. DQ in total, we know that OQ is the radius of this circle, that equals to 2. So in total, DQ equals to 1 plus 2, that is 3. And again, AD is 1, DQ is 3, and it is equals to CD. CD is the missing side, so we leave it as it is, times dp. dp equals to the square root of 5 units in its length. So in total, we found out that according to all 24, 1 times 3 equals to CD times square root of 5. So 1 times 3 is 3, so 3 equals to square root of 5 times CD. So here we will divide this equation by square root of 5 and finally get that CD, the missing sign CD equals to 3 over square root of 5 units in its length. Okay, this is the missing side CD, is equals to 3 over square root of 5 units in its length. So write it down. So now we can implement the Pythagoras theorem on this right angle DCB in order to find out the length of this missing side, side CB. And the area of the green shape equals to the area of the right green triangle DCB, that is to say, it will be equal to the base DC times the height CB over 2. This is the area of the green shape. Okay, so first of all, we will implement the Pythagoras theorem on this right triangle DBC. So on right triangle DBC, here by PT is a relation for Pythagoras theorem. dB squared, that is the square of the hypotenuse, equals to DC squared plus CB squared. And again, according to the Pythagoras theorem, on this green right triangle DCB, this is actually the area that we are looking for, this green right triangle DCB. This is the area of the green shape. So in the right triangle DBC, according to the Pythagoras theorem, dB squared, that is the square of the hypotenuse, equals to DC squared plus CB squared. The hypotenuse dB equals to square root of 5, and therefore dB squared is square root of 5 squared, that is 5. And it is equals to DC squared. DC is 3 over square root of 5, and therefore this C squared is 3 over square root of 5 squared. 3 over square root of 5 squared equals to 3 squared, that is 9, over square root of 5 squared, that is 5. So that 3 over square root of 5 squared is 9/5. Yeah. 3 over square root of 5 squared equals to 9/5. plus CB square. CB is the missing side, so here this it is. So total, if you found out that 5 equals to 9/5 plus CB square. Here we subtract 9/5 from this equation, and we get that 5 minus 9/5 equals to CB square. Here we will multiply 5 by 5 and then we will divide it by 5 in order to overcome part of this number. So 5 times 5 is 5 over 5. We multiply it by 5 and then we divide it by 5, so we change nothing. So it is 25 over 5 minus 9 equals to CB square. 25 minus 9 is 16, so in total this expression equals to 16/5. So in total if you found out that 16/5 equals to CB square, here we take out of this equation and finally get that CB, the missing sign CB, is equal to the square root of 16, that is 4, over square root of 5. And again, if you found out that the missing side CB is equal to 4 over square root of 5, it's in its left. This is the missing side CB is equal to 4 over square root of 5 units in its length. And again, our task is to find out the area of this relationship, that is actually the area of this right great triangle DCB. So the area of the green shape is equal to the area of this right great triangle DCB, and the area of this right triangle DCB equals to the base of this triangle, that is DC, times the height, that is CB, over 2. Why the height is CB? Because it creates 90 degrees with the base DC. So in total, if you found out that the area of the green shape equals to the area of the green right triangle DCB, and the area of the green right triangle DCB in total equals to the base, that is DC, times the height, that is CB, over 2. So DC is 3 over square root of 5 times CB. CB is 5 over square root of 5. It is 4 over square root of 5. And we have to divide it by 2. It is the base times the height over 2. And again, in total, if you found out that the area of the green shape equals to the base, that is 4 over square root of 5, times the height to the base, that is 4 over square root of 5, divided by 2. So here we have, in the numerator of those two expressions, we have 3 times 4, that is 12. And here we have square root of 5 times square root of 5, that is 5. And we have to divide it by 2. So the area of the green shape in total equals to 12 over 5. Here we remove the 2 to the numerator. So in total, the area of the green shape equals to 12 over 5 times 2, that is 10. So 12, the area of the green shape equals to 12 tenths. Or it is equals to 1.2 square units in its size. Because again, if we found out that the area that we are looking for this question, that is the area of this green shape in total is equal to 1.2 square units in its size. So we finished to answer this question. So in the next step, answer the lecture. So our task in this lecture is to find out the area of this green shape, that is actually the green right triangle DCB. So again, our task in this question is to find out the area of this green shape, that is the area of this green right triangle, DCB. Okay, so in the drawing we have the quarter circle AOB. In the drawing we have the quarter circle AOB. It is given us a question that AD equals to DO. This is the side OB equals to 2 units in its length, according to what is given us the question. We also know that this is angle DCB, this is a right angle, and therefore the right angle, the green triangle DCB is the right angle. Again, our test is to find out the area of this green shape, that is actually the area of this green right triangle DCB. First of all, AOB is a quarter circle, and therefore this is the right angle. OB is the radius of this quarter circle, that equals to 2. Likewise, OA is also the radius, therefore it is equals to 2. The radius OA has been bisected into 2 halves at this point, point D. So the first half of the radius AO is AD, that equals to 2 over 2, and the force equals to the second half of the radius AO, that is also equals to 2 over 2, that is 1. So each half equals to 1. AD equals to 1, and D also equals to 1. Okay. So in the next step, first of all, we implemented the Pythagoras theorem on this right triangle DOB. According to the Pythagoras theorem, in a right triangle, the square of the opponent equals to the sum of the squares of the perpendiculars. So in this right triangle DOB, DB squared, that is the square of the hypotenuse, equals to DO squared plus OB squared. And again, according to the Pythagoras theorem, in the right triangle DOB, DB squared, that is the square of the hypotenuse, equals to DO squared plus OB squared. DB is the missing side, so so it is DB squared equals to DO squared. DO is 1, therefore DO squared is 1 squared, that is 1, plus OB squared. OB is 2, therefore OB squared is 2 squared, that is 4. So DB squared equals to 1 plus 4, that is 5. So DB squared equals to 5. Here we took out of this equation and found out that the length of the hypotenuse DB is equal to the square root of 5 units. This is the hypotenuse DB of this right triangle DOB, and it is equal to the square root of 5 units in its length. In the next step, we completed this quarter circle to a circle, and then we extended the radius BO until it touches the circle. We define the touching point of the extended radius BO with this circle. This point is point P. OP is, of course, the radius of the circle, that equals to 2. And because of the fact that, first of all, we extended radius BO by straight line. The radius is a straight line, and we extended straight line by straight line. The result BP also must be a straight line. And because of the fact that BP is a straight line, therefore BP is a chord. But BP is a chord that passes through point O, that is the center of this circle, and therefore BP is the diameter of the circle. Because we know that the diameter of any circle must pass through the center of the circle, and therefore, because of the fact that chord PB passes through point O, that is the center of the circle, PB is the diameter of this circle. In the next step, we extended the radius AO until it touches the circle at this point Q. We extended side CD by straight line until it touches the circle. But the question is, where the extended side CD will touch the circle. We assume that the extended side CD will touch the circle at this point, point Q. but here it is impossible that the extended side CD will touch the circle at point Q because of the fact that then we have triangle BCQ that is equal to 90 degrees inside, and still it doesn't subtend on the diameter of the circle because BQ is definitely not the diameter of the circle because it doesn't pass from point O to the center of the circle. Likewise, we assume that the extended side CD will touch the circle at this point N. But it is impossible that the extended side CD will touch the circle at point N. Why? Then we will have triangle BCN. This is equal to 90 degrees inside. Triangle BCN, subset on called BN. This is called BN. That is definitely not the diameter of the circle because of the fact that called BN doesn't pass from point O, that is the center of the circle. So, due to those contradictions to rule 5, we will derive that the extended side CD will touch the circle at point P and not in another point because then we will have contradiction to all 5. But here we have triangle BCP is equal to 90 degrees inside, and indeed triangle BCP subtend of chord PB, that is the diameter of this circle. It is exactly according to rule 5. Okay. So here we have OP is the radius of this circle, this equals to 2, OB equals to 1, and therefore the hypotenuse here must be equal to the square root of 5, because those two triangles can go into each other. The hypotenuse of this triangle DB is 4, therefore the hypotenuse of this triangle DP must be also equal to square root of 5 because of the fact that those two triangles can go into each other according to side angle side rule. So PD equals to the square root of 5 minutes and it's left. So here we can implement all 24. Here, this is called AQ. Intersect with code CP, it's point D. Again, code AQ intersect with code CP, it's point D. So all the requirements of all 24 are satisfied, and therefore we can implement here all 24. Quit again. In our original drawing, we have code AQ that intersects with code CP, it's point Q. It's point D again. Code AQ intersects with code CP, it's point D. So all the requirements for full again, code AQ intersects with code CP, it's point D. So all the requirements for full 24 are satisfied, and therefore we can implement here all 24. According to all 24, the following equation is true. That AD times DQ equals to CD times DP. Again, AD times DQ equals to CD times DP. And again, according to all 24, the following equation is true. That AD times DQ equals to CD times DP. AD is 1. Here, OQ is the radius of this circle and it equals to 2. So AD is 1, DQ is 1 plus 2, that is 3. And again, AD is 1 and DQ is 3. And it equals to CD, CD is the missing side, so it is, times DP. DP is equals to the square root of 5 units in this line. And CD is the missing side, so it is, times DP. DP equals to the square root of 5 units in this line. So to that, we should find out that 1 times 3 equals to CD times square root of 5. 1 times 3 is 3, so 3 equals to square root of 5 times CD. Again, 3 equals to the square root of 5 times CD. Here we divided the equation by square root of 5 and found out that the missing side CD equals to 3 over square root of 5 units in its length. This is the missing side CD. This is equals to 3 over square root of 5 units in its length. So now we can implement the Pythagoras theorem on this green rectangle CDP in order to find out. Implement the Pythagoras theorem on this green rectangle CDB in order to find out the length of this missing side CB. So according to the Pythagoras theorem, in this rectangle CDB, DB squared, that is the square of the hypotenuse, equals to DC squared plus CB squared. And again, according to the Pythagoras theorem, in this one again CDB, DB squared, that is the square of the hypotenuse, equals to DC squared plus CB squared. And again, DB squared, that is the square of the hypotenuse, equals to DC squared plus CB squared. DB squared, that is the square of the hypotenuse, equals to DC squared plus CB squared. DB equals to the square root of 5, therefore DB squared is equal to 5 squared, that is 5. And DB in total equals, DB squared equals to, in total to 5. And it is equals to DC squared. DC equals to 3 over square root of 5. And therefore DC squared equals to 3 over square root of 5 squared, that is 9/5. So in total DC squared equals to 9/5 plus CB squared. CB is the missing side, so it is. We leave it as it is. So in total, if we found out that 5 equals to 9/5 plus CB squared. Here we subtract 9/5 from this equation. If I found out that 5 minus 9/5 equals to CB squared. So here we multiply this number by 5 and then we divide it by 5 in order to overcome factor with this number. So 5 times 5 is 5, and we have to divide it by 5. So in total, we have here 25 over 5 minus 9/5. So it is minus 9/5 equals to CB squared. 25 minus 9 is 16, so in total this expression equals to 16/5 equals to CB squared. Again, 16/5 equals to CB squared. So here we took out all those equations. If I found out that CB equals to the square root of 16, that is 4 over square root of 5. So in total, CB equals to the square root of 16, that is 4 over square root of 5. Again, CB equals to 4 over square root of 5 units in its time. This is the missing side CB, this is equals to 4 over square root of 5 units in its time. So our task is to find out the area of this green shape, that is the area of this green right triangle, DCB. The area of this green right triangle, DCB, equals to the base DC times the height CB over 2. Why the height is CB? Because it creates 90 degrees with the base CD. This is a right angle. So in total, the area of this green shape equals to the area of this green right triangle, DCB, is equals to the base DC times the height CB over 2. The area of the green shape in total equals to the base of the green triangle DCB, this is DC, times the height CB over 2. We already found out that DC equals to 3 over square root of 5, and CB equals to 4 over square root of 5. Again, DC equals to 3 over square root of 5, and CB equals to 4 over square root of 5, divided by 2. Here we have 3 times 4 is 12, square root of 5 times square root of 5 is 5 over 2. So here we have 12 over 5 over 2. So here we move the 2 to the denominator, and in total this expression equals to 12 over 5 times 2. 5 times 2 is 10, so in total this expression equals to 12 tenths. In terms of numbers, it is equals to 1.2 square units in size. So in total, if you found out the area that we are looking for this question, that is the area of this green shape, it is equals to 1.2 square units in its size. Okay, thank you very much.